here. It takes a few minutes, and I think we're live. So welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we're presenting efficient trajectory calculation for extreme mass radiation spirals and orbital resonances by Philip Lynch. Philip did his bachelor's in theoretical physics at University College Dublin, where he also got his PhD in applied and computational mathematics, and he graduated in 2022. He's now at Potsdam at the Albert Einstein Institute in Germany, and his research focuses on the evolution of binary system consisting of a stellar mass black hole, or a neutron star, and a supermassive black hole. And this is what is known as an extreme mass radiation spiral. So he's an expert on resonances and many of the details that are very complicated on this problem. And today we will have a glance at one of his latest interests and results. Remember, you can ask questions over email, through YouTube channel, or Twitter, or these days called X. And then the questions will be read at the end of the talk. So without further ado, we will turn the time over to Philip. Thanks for joining us.
Right, thank you for that very nice introduction. So I will just start here, and hopefully everything will work fine. There we go. Perfect. Yep. So apologies for the mouthful of a title. I'm hoping that by the end, this will all start to make sense. But to kind of put everything in context, I want to start by, saying what a wonderful time we live in to be in the era of gravitational wave astronomy. We're now at the point where we can detect these ripples in space-time emerging from merging either black holes or neutron stars that are happening light years away. And it's now getting to the point where we've seen so many of these things, they're almost becoming boring. I mean, the last LIGO catalog clocked in over nearly 100 sources. And, with the current LIGO run 04, we're seeing dozens and dozens more of these things. But importantly, I've plotted one of the signals here. What you'll notice is that the signals that we see are generally pretty short. They span maybe seconds, maybe a few dozen seconds, maybe up to a minute or so. And that's because we're only really seeing the very last part of the inspiral and then the merger here and then the ring down. And that's largely because of the sensitivity of current ground-based detectors. So that currently ranges between 10 and, say, 10,000 hertz. And in many ways, this is restricted, not because the engineers have done a bad job or anything like that, far from it, but just because they're detectors on the Earth, and the Earth, shakes, vibrates, and these are oscillations that are very difficult to get rid of at the lower frequency range. So what we can do to get around this is put our gravitational wave detectors in space, and we'll hopefully come and see various space-based detectors that will come online in the 2030s, including the European Space Agency's LISA mission and the two Chinese missions, Changqing and Taji, although the LISA has now been formally adopted and has a formal date for 2035, and I'm very involved in, so I'm very excited about that. In many ways, it seems like a long time away. It's over a decade away still, but there is still a lot of work that needs to be done before that. But importantly, because these things are no longer on Earth, they can now probe frequency ranges that are much, much lower, going between 0.1 millihertz up to 1 hertz. And so it allows us to see not only the early parts of the inspirals that we're already seeing in ground-based detectors, but it also allows us to see entirely new sources. So these will be things like merging supermassive black holes, white dwarf binaries that are currently in our galaxy, potentially a gravitational wave cosmological background. But there's one source that's very near and dear to my heart that I think has a lot of potential for a lot of interesting science, and these are extreme mass ratio inspirals. They're so called because, as was explained before, these consist of a massive black hole, something on the order of millions of solar masses, and a compact object, usually a black hole or a neutron star, that's on the order of maybe a solar mass to maybe tens of solar masses. And the ratio between these two masses is rather extreme, right? Ranging anywhere from 10 to -4, 10 to -7. And the idea is that as the small object is orbiting the larger object, you connect these very complicated orbits, as we see in the animation here. And as it spirals in, it loses energy and angular momentum in the form of gravitational waves, which will be detectable by LISA for potentially months or years. So these are incredibly long signals. We'll have potentially millions of orbital cycles that we need to resolve. So this is actually a very difficult system to try and model. And there are many approaches for doing this. Importantly, we also have very strict requirements. In order to do the sort of science you want to do, like precision parameter estimation of supermassive black holes and these really stringent tests of general relativity, we're going to need to achieve three important things. So the first thing is that the model's got to have all of the physics we would actually expect of a typical astrophysical EMRI, which means it's got to include spin precession and orbital eccentricity. It's also got to be fast to evaluate, so ideally in less than a second, and it also has to be accurate to with a phase accuracy within a fraction of a radian, or something that's roughly in the ballpark of 1 over the SNR of these signals. And the max SNR we might see is maybe on the order of 100. So being able to do 2 of the 3 of these things isn't too bad. Being able to do all 3 is really, really difficult. It's a huge challenge. And so the way we go about modeling the systems is to look at the relativistic two-body problem. And there are many other things that have been used for other sources of this type, like say, merging black holes that we already see in LIGO. And there's a variety of approaches one could do. One could try and, like, say, for instance, solve the Einstein field equations numerically, which is the role of numerical relativity. And this is generally speaking down in this lower right corner of this plot, where here we have the compactness of the source. If it's up here, it's very, very far away. They have large separations and the field is very weak. And here we have the mass ratio, where up here we have things that are like a 1-to-1 mass ratio, like we already see in LIGO. And out here we have things that we see in EMRis. But EMRis encompassing essentially all of this part of the parameter space here. So NR can really only ever do this corner due to the computational limitations and things like the resolution and the step size, these sorts of things. So it's somewhat limited there. If you go out to the weak field, however, you can use the post-Newtonian expansion and expand in powers of V over C and the gravitational constant G, and that'll do very well out in the weak field where the sources are moving slowly. If you have things like scattering orbits, you can also use the post-Minkowskian expansion, which is exact in V but expands in G, which is really nice if you have these hyperbolic encounters or very eccentric sources, these sorts of things. But you'll notice that that won't get us into the strong field where EMRIs will be. There has been work to try and get information from all of these things, which is the use of effective one-body models, which try and combine information from all of them to have one sort of master model. But it's still, at the moment anyway, missing a lot of information from this corner that we're most interested in. And so here, if you want to model EMRIs in particular, which go from here to here, the only game in town is really the gravitational self-force method, where one expands in powers of the small mass over the large mass. And so the general principle that I'm very much oversimplifying is you have equation of motion that looks a lot like what you might see in your undergrad GR course. This is just the geodesic equation, where in principle, the Christoffel symbols here are those going to be given by the space-time of your large black hole. If it's not spinning, it's Schwarzschild, and if it is spinning, it's Kerr, and it gets slightly more difficult. But in principle, we have a good handle on how to use this. And then you'll notice that you have a bunch of stuff over here that is no longer zero. And the reason being is that if it was just zero, it'd be a test particle following a a time-like geodesic in the space-time, and that's very straightforward. But because this thing is a black hole or a neutron star, it has its own gravitational field. And the presence of this gravitational field interacts, is going to cause things like gravitational wave emission, and it interacts with the black hole space-time. And so it ends up being pushed away from geodesic motion. In a sense, it's experiencing a force due to its own gravitational field, which we dub the gravitational self-force. So in order to know how far in this expansion in the small mass ratio we need to go, like do we need epsilon cubed or epsilon to the fourth, when do we know when we can stop and get things that are accurate enough for LISA? There was a really, really good paper by Hinder and Flanagan back in 2008 that looked at the orbital phase, which corresponds to the waveform phase, and looked at what parts of the self-force you would need at each order in order to accurately describe this phase. So you can see that if all you care about is getting the leading order effect, well, then one can get away with so-called adiabatic inspirals, or in this order counting, it's called 0th order post-adiabatic, which is a bit of a funny way of putting it. It makes more sense when you go to the higher orders, though. Or you can just say adiabatic, right? And for that, you can either use just the dissipative piece of the first order self-force, or what's significantly easier, and what's usually done in practice, is you look at the flux of energy and angular momentum coming out of the particle and is radiated to infinity and then the horizon. We have ways of doing this quite simply from the Tucholsky equation, and that is a significantly easier way of doing it. And via flux balance law, you can say how much energy and angular momentum is lost by the secondary and how it spirals in. And so adiabatic waveforms are fairly well produced. There's a lot of work in producing these that will be accurate and fast enough through the fast EMRI waveforms package. And they have a good amount of parameter space coverage as of right now. So we have a good handle on this. However, if all you have is an adiabatic waveform, well, you're going to miss out on things that come in at order 1. So you'll have an error that's, of order 1, but it could end up being tens of radians or hundreds potentially on the initial conditions and these sorts of things. So ideally, you'd want to get to the next order in this order counting, and that is this term here, the post-adiabatic correction. And this is significantly harder to get because not only do you need all the information from the first order self-force, you're also going to need some information from the second order self-force. And going to linear order in perturbation theory, as anyone who's ever done a Taylor expansion will know, is a lot easier than going to the next order. So I can't do justice to how difficult a calculation this is. There are currently some exciting results coming out that so far can only do the simplest system with a non-spinning primary and a secondary that's in a circular orbit, which has shown really good agreement with numerical relativity. It's very exciting, but currently there's a long way to go before it can include things like eccentricity and spin precession, like what I was talking about before. But also importantly, since we know that once we get this, we'll have an error that scales roughly with the mass ratio. And for an EMRI, that's very, very small. And so we figure at this point, it's sufficient. That's enough. We probably don't need third order, anything too crazy. What I'm neglecting to mention is this thing in the middle. So this thing that scales, in between the two with epsilon to the power of -1/2. This is a thing that you only have to worry about once you have both eccentricity and spin precession in your system, because then we have a thing known as orbital resonances, which will be the focus of this talk going forward. Essentially, the argument is that, well, if we need to know this term, then we really need to get this term under control as well. And so this is what I'm looking to do. So generally speaking, the ways for getting an EMRI waveform out of a self-force calculation follows 3, I'm putting easy in quotation marks because they're not very easy at all, but it's roughly 3 steps. The idea is that you're going to do a self-force calculation, ideally at say 1 point in parameter space. You might have to do this at multiple points to generate a model you can then interpolate and evaluate rapidly at the in-between points or something along those lines. But for now, because we're lacking a lot of the information for generic care orbits, we're going to have to rely on a toy model for the self-force. But once you have your force model, this gets fed into some way of calculating the trajectory of the inspiral. And so there's been some use of the 2 timescale expansion and current second order calculations. But for this work, the most mature framework is using osculating geodesics, or more colloquially known as osculating orbital elements, when it was used back in classical mechanics. And then the idea is that once you have your inspiral, you can then feed that into some sort of waveform generator. And in principle, we'd also use Tucholsky-based amplitudes that come from the Tucholsky equation. But again, these are numerical. We need to interpolate them across the parameter space, and they just aren't quite ready in a usable form in time for this project. So we're just going to approximate the waveform using a quadrupole waveform instead. So here we're using, we're kind of compromising on what we have out here and out here. And the reason being is that we're really just focused on this middle step here. This is where we currently have a huge bottleneck, and we want to really try and speed this up using various averaging techniques, because as we'll see as we go forward. So a lot of work was done, including things like eccentricity and spin precession. This all actually started for eccentric orbits around a Schwarzschild black hole when my supervisor, Niels Wolverton, and my collaborator, Martin van der Meent, first laid out the framework for using near-identity averaging transformations for extreme mass ratio inspirals, which can really speed up these trajectories. And then it was brought late to me as a young PhD student to try and extend this out to care. So we have our first paper on this, shortly after that. Then we decided to look at, okay, well, what happens if we don't have eccentricity, but we have spin precession? And so we're in this case here. And so we did a paper on that as well. So finally, the final challenge of this is what happens when you have both eccentricity and spin precession. And this was the thing that, the final chapter of my PhD thesis where we just about got this done before I submitted. It was great to get through that. And there are a couple of complications that arise. There was some simultaneous work where I also looked at adding some effects from the secondary spin with a group from MIT. But the main bulk and the main reason why this takes so long is because you also have to treat orbital resonances very, very carefully. And this is what you get when you end up in this phase. So as if this wasn't already complicated enough, there's an extra sneaky step involved in all of this too. All right. So let's just turn off the gravitational self-force. Imagine we are just a test particle in a background space-time around a black hole. What are the geodesics like? What's the easiest thing like? Well, thankfully, while the orbits do look very complicated, we actually have a very good handle on how to describe them. So ideally, your orbit is going to evolve between a minimum and a maximum radius, so just bob in and out this way. And it's going to bob up and down between a minimum and maximum value of your inclination angle. And then also, as it does so, it's going to also spin around this axis too. And you can see it carve out parts of the parameter space here. So we parameterize each orbit using the semi-lattice rectum, which is related to those roots, the eccentricity, and this particular measure of inclination, just because that's the convention that's used in a lot of these calculations, which we call x, right? We're also going to, instead of using the proper time that you might be familiar with, right? The time that the secondary experiences. We're going to instead use this related quantity known as Mino time, which was first developed purely to, it doesn't have any physical meaning like Mino time does, or coordinate time, which is what an observer at infinity does, but it's merely a mathematical trick that allows us to decouple the radial and polar motions from each other so that we can get analytic solutions for each if we do things in this time, particularly if we use Mino time action angles. These are particularly nice because these are just tell you, they kind of parameterize your phase, like where in the bobbing between R1 and R2 you are is the radial phase, where in the bobbing between here and here you are is the azimuthal phase, the polar phase, and the azimuthal phase is how far around this way you're going. And what's nice is that the rate of change respect to Mino time is a fundamental frequency of that orbit. It depends only on these constants, PE and X, which is going to be very useful for the calculations we do later. And importantly, we use these parameterizations because we have analytic solutions for these orbits. So this is all perfectly controlled. This is fine. We know how to deal with just geodesics. But how do we go from a geodesic to an inspiral, the thing we really care about? So for this, we use the method of osculating geodesics, or you may have heard it as osculating orbital elements, or variation of parameters, like these other names for it. And the idea is that you're going to identify some constants of motion, which in our case are PE and X. We also need the initial starting point of our phases, in particular, the radial and polar phase, QR and QZ. And we group these together as a set of orbital elements, which go now from being constants to functions of time. And so long as we impose the osculating conditions, which is that your inspiral trajectory can be mapped to that of a geodesic, and its coordinates and its four velocities can be mapped to that of a geodesic, you can then derive equations of motion for the orbital elements. So you can get the evolution equations for these. And importantly, this doesn't make a small mass ratio approximation. In principle, it's valid for any force model that's acting on the system. But the tricky thing is, as I alluded to, what force model are we going to use for our generic inspirals? Because we don't have second order self force. And while we do have first order self force, Martin has a code that produces this, it's way too expensive. It takes on the order, I think, of like hundreds or thousands of CPU hours to generate one point, which is why he's only ever run it like 6 times in the paper where he announced that he got this result, which is a pretty landmark paper in itself. But we would need to, we need to evaluate it potentially hundreds of times in order to interpolate over a small region of parameter space to get a model that's rapid to use. And so even just doing that step is too expensive. So what we do is we're going to take some of the work we did before, where we looked at purely eccentric equatorial and then circular but inclined orbits, where we have interpolated models for the self-force in those cases, and we're just going to stitch these together. So the end thing is very much unphysical, but it has roughly the right kind of behavior in the equatorial plane, and well, it reduces to the right behavior in these two limits, and it has both eccentric corrections and spin precession corrections. So it should have roughly the right kind of behavior. And because we're just making stuff up at first order, we might as well just make up the second order part too. Again, emphasizing that the results we have here don't say us anything about astrophysical EMRis. They tell us a lot about the approach we should use. And once we have the actual correct models for the cell force, they can just be slotted into this calculation and nothing else down the chain would have to actually change. But just, it's good to get ahead of that point right away. So we have our force model, and we're going to stick this into the oscillating geodesics. And so we end up with equations of motion that look like this. So our orbital elements are capital P's. These go from being constants to things that now slowly evolve with time. Our orbital phases now go from things that just went with the orbital frequencies, but now also have a correction. And our extrinsic quantities that we need to carry around, which are just the t and phi coordinates of the particle. We just need those to generate the waveform at the very end. So this is their evolution is just given by the geodesic equation in the oscillating geodesic scheme. So it actually makes that bit very simple. And so we can then go and produce an inspiral with this. So what I've done here is I've shown one for an eccentric equatorial orbit where we have an initial semi-last rectum, an initial separation, and some initial eccentricity that starts all the way up here. And the idea is that, well, I might start all the way up here, right? As the orbit then evolves, it's going to shrink, right? So the semi-last rectum is going to decrease going this way, but it's also going to circularize, meaning that it's going to decrease this way as well. So it follows this trajectory here up until it reaches this dashed line, which is like the last stable orbit, where the oscillating geodesic approach breaks down. Because there are no longer any closed form geodesics for it to map to. So you can't use it past this point to describe the transition to plunge and then plunge and merger. So we have to cut off our inspiral a bit soon, but that's fine because for an EMRI, we don't really need the last bit. Unlike the shorter waveforms that we see in LIGO, for EMRIs, we have so much inspiral to work with that most of our SNR is going to come from there. And so we can kind of truncate our inspirals a little bit early. Although in principle, it would be nice to then go and add this on as well. But we're talking about something that lasts for years out here, and then something that's probably on the order of like maybe a couple of days at the end. So it's not the end of the world if you miss this last bit of inspiral. Okay, so you have your inspiral trajectory, and it all looks great. The problem is when you run this code, you notice that it takes a really long time to finish, like a really long time, potentially like minutes, hours. When the orbits get really complicated, it can even take on the order of days. And the reason for that is, while it all looks nice and smooth here, once you zoom in, you realize you have all these tiny little orbital oscillations. And these are such a pain for any sort of numeric solver that's trying to solve these numerically, because it's got to take these tiny step sizes to resolve them. And the reason why you have these oscillations is that our equations of motion depend on the rapidly oscillating orbital phases as opposed to the slowly evolving constants of motion. So this is a huge pain, but thankfully there is a way to get rid of these. And this is using the method of near identity averaging transformations, lovingly abbreviated to NITs. And I'm also going to be a bit suggestive here and say these are the full NITs, that we're going to get rid of all of the oscillations here. But the idea is that we're going to transform to new variables. So instead of evolving our P's, our Q's, and the S's here, we instead evolve these P tilde, Q tilde, and S tilde that are related to the original ones, plus some periodic functions that scale with order of mass ratio that we kind of leave arbitrary. And the idea is that as we go through the steps of finding the equations of motion for the tilted variables, we use these functions to cancel out any oscillatory terms so that one, we end up with the average equations of motion, but two, we constrain what these functions have to be so we can relate the oscillating system to the average one, which can be very useful down the line. And also what's nice is that it also breaks up where all the contributions come from. So like here, you can very clearly see that these are the things that come from just that geodesic motion I showed you before. Then here, this term here, the rate of change of say your P and X at leading order is your adiabatic term, right? Which will get you, some of the way there to getting an EMRI waveform, but not fully. And then to get all the way to post-adiabatic, we need to include these additional terms as well in our equations of motion. So I'll give you a little flavor for how this works because it sounds very vague and hand-wavy. So the idea is that you use the equations of motion that I showed before, along with the transformation at linear order. So we're just going to do the very first step in this calculation. I want to find what this forcing term is in terms of the original forcing function I had before. So that by definition, at least at this order and mass ratio, because I want to compare everything at the same order in perturbation theory. Well, that is just by definition 1 over epsilon, right? I'm bringing the epsilon over this side, times the rate of change of this p tilde, right? And p tilde, if I remember correctly, is at linear order in the transformation I showed before. It's our original p plus this correction term that comes in here. And so the rate of change of this p was just the original function we had, plus, and then we, at linear order, we just get the rate of change of this thing is just 1 over, and the rate of change with respect to the orbital phases times the rate of change of those phases with respect to lambda, which is the orbital frequencies that I showed before. Of course, there are corrections due to the fact that it also depends on the orbital elements, and those also evolve. That comes in at the next order of perturbation theory, so we don't have to worry about it at this step. We do have to worry about it at the next step, which we won't do, don't worry. So we then split everything into average pieces and oscillating pieces. So the average pieces, which I denote with the angle brackets here, these only depend on your slowly evolving orbital elements. And then your oscillating pieces, these we're going to Fourier decompose into its various modes and will depend on the rapidly oscillating phases like such, but it will have no orbit average. So we then expand this out, right? The average piece of this is given here, and the oscillating piece of this is given here. And then this function is a purely oscillatory function, right? And it's given by this expression here. And so if I want just something that only depends on the orbital elements p, and I don't want anything that depends on q, I gotta make these two terms cancel out. And the way I do that is I constrain that this transformation term has to have this value, and that the overall value of f tilde 1 is the orbit average of what we had before. Now, of course, this worked out very simply, but it gets much more complicated as one goes to higher orders, and I will not torture you with that for now. If you do want to torture yourself with that, you can see the full details, which are in the original work by Martin and Niels, linked here. But that's the general principle. So I'll give you the results of all of this. The idea is that the very first terms in these equations of motion that we need, a lot of them end up being very straightforward. They just correspond to orbit averaging their corresponding term in the oscillatory system. But these terms are a little bit more complicated because not only do they have a term that might be related to its corresponding average, they also have a term that's related to this operator, which I've suggestively called n, like this kind of knit operator, which is not in terms of something as simple as the orbit average, but is instead a function of all the Fourier modes of the other functions in the system. And it looks something like this, which is a huge mess, like this n operator acting on some function a. You don't have to memorize all this, but just know that it can be worked out. It's not too bad, even if it does look a little bit ugly in this form when it's expanded out. But in principle, we can get a good control on this so long as we can take all our functions and Fourier decompose them. We can then sum them together in this very precise way and get the contribution that should come in at this order. So how we actually do this in practice involves first a series of offline steps. So we have to first make a choice about our parameter space and how we're going to grid it up. This means taking a bunch of values of P, E, and X and deciding how densely to grid it and that sort of thing. And then at each point in this parameter space grid, we're going to take all our functions of the equations of motion. We're going to perform a fast Fourier transform on all of them. And then we're also going to take their derivatives with respect to the orbital elements and take the fast Fourier transforms of those as well, because we also need those modes too. And then we use the equations I showed on the previous screen to combine these together to get the things that we needed for, the averaged equations of motion, f tilde 1, f tilde 2, and so on. And then everything else we actually know analytically in those equations of motion, which is very nice. But then once we have this at one point, we repeat it across the grid. And so we then end up with a grid of values for each of these functions. And then we just interpolate these with Mathematica and we save those interpolants. So we have numerical interpolants for all the averaged functions in our equations of motion. And then so this can be quite costly. This can cost, several hours, maybe a day or two on a cluster, in my very unoptimized Mathematica code, I should add. So it can definitely be done faster. But the online steps, by comparison, are actually very, very quick. All you have to do is just load in your interpolants into your environment, set your initial conditions by taking the transformation I showed before and inverting it to leading order, right? And then once you have your initial conditions and you have everything loaded in, you can just numerically solve this. And the solver will fly through these trajectory calculations very, very quickly, usually in less than a second. So this last step is very, very quick. So to give you an idea of what this ends up looking like, I decided to plot the trajectory of what's not really an EMRI because it's a very, very large mass ratio. The oscillations involve scale with mass ratio. So I've decided to pick one which has a mass ratio of 10 to negative 2 so that you can actually see them by eye and get an idea of what's going on here. So for generic care orbits, as you can see, these oscillations get really messy and complicated. So using just the method of osculating geodesics, which I've lovingly called OG here, you have the blue curve, and as you can see, it's going haywire, right? But it's still evolving a trajectory, starting up here and then evolving downwards, as we saw before. But if we then go and use our average equation of motion from the near identity transformations, that is that orange curve that just goes right through it. It'll just glide right on through. And to kind of prove that everything is being kept roughly in phase, what we can do is we can put the oscillations back on, in a sense, by just inverting the near identity transformation to linear order and just put them back on. And we can see that it remains in phase very well. Right? And that's what the dash red line tells you, that we can like reconstruct the oscillations if we need to, which usually we actually don't for the waveform calculations, but it's a nice way of proving that everything's staying in phase. And because, one data point does not a theory prove, we do a bunch of convergence tests to prove that everything is scaling in the way predicted by the theory with our numerical implementation. And so what we have here is we evolve things with the oscillating geodesics, use the full knit, going through the same patch of parameter space, right, between two fixed points, I believe like a P of 7 and P of 4, something like, no, actually, no, this is out of a P of 10 and a P of 9. And so the idea is that it evolves through the same patch of parameter space each time, and we compare this to our full knit that we used before. Specifically, in this case, we also invert the knit and put the oscillation back on and look at that difference. And we expect that this should scale as order mass ratio squared. And we can see the scaling recovered on this log plot here. And for the orbital phases, right, our QRs, QZs, and our extrinsic quantities, the T and phi, right, similarly, the equations of motion should only be accurate with a scaling that should scale linearly with mass ratio. And we see that we also recover that linear mass ratio scaling here. So great, everything looks great. And then if we look at how long everything takes in terms of timing, if you were to run the same calculations for using oscillating geodesics, you'll see that for comparable mass ratios, it's not too bad, I guess. But as you go to more and more extreme mass ratios, you have to resolve more and more orbital cycles. And after a certain point, right, I just gave up because this was taking too long. So I didn't bother plotting what would happen out here because it's already taking thousands of seconds. I just didn't want to wait that long. But you can see that if you use the full knit, that we're looking at things that can evolve with like a fraction of a second every single time in a way that's independent of mass ratio, telling us that our adaptive time stepper is just, stepping right through all these oscillations and doesn't care about them, which is really good to see. So it seems like everything's working. Our calculations are very efficient. We have efficient trajectories for extreme mass ratio inspirals. Surely the talk should just end here. We've done it. Unfortunately, there was also a second part of this talk, and we'll see what problems arise if I just take the exact same procedure and just look at a different part of parameter space. And that is what we get here. As you can see, things have clearly gone dramatically wrong. It's very confusing to see what has just happened, but essentially, if you then look at these same convergence plots, you get kind of a hint, right? And so the idea is that if we look at the same convergence plots again, we see our initial scaling with mass ratio squares that we saw before. As we go to smaller and smaller mass ratios, tends to level off to something that scales with epsilon to the power of a half, like the square root of the mass ratio, roughly. And then also for the phases, right? So that actually doesn't seem too bad, right? Because the square root of epsilon is still a pretty small number. But if we look at the phases, we go from something that scales linearly with the mass ratio to something that scales with 1 over the square root of the mass ratio. So as we go to smaller and smaller mass ratios, we accumulate more and more phase error. So this is terrible. None of the data analysis we'll be able to do, and the nice ELISA science we want to get out, is going to be possible with waveforms that are this bad, unfortunately. So what has happened here is that we've hit an orbital resonance as we went through this patch of parameter space. And so this is when the radial frequency that I showed before is an integer ratio of the azimuth, or the polar frequency, I should say, and that this is a linear combination that equals 0 for a particular n and m at one part in parameter space. And so there's also this like resonant phase combination of the two phases that is the same n and m as the one that, gives you 0 here, which I'm going to define as q perpendicular. It's worth remembering this now. But as predicted in a paper also by Hinder and Flanagan, but like a year or so later, in 2009, that you can have these resonances that will cause jumps in your orbital elements that scale roughly as epsilon to the half, and produce a phase error that scale as epsilon to the minus a half. So we've managed to like numerically recreate those findings that they derived or predicted analytically. And so it's not just the fact that we have terms that are 1 over this thing. Fundamentally, what is happening is that the definition of an orbit average is changing. When you had just a standard generic orbit, right, it would look like this blue one up here. And if you plot its trajectory through phase space and you do it for long enough, it would ergodically fill this phase space. So for a given geodesic, you could equate the orbit average of any quantity, right, over an infinite Mino time with that of just the torus average. Or even more succinctly, if you're fast Fourier transforming everything, just the zeroth mode you get out, right? Which makes things very convenient. However, if one goes through a resonance, things are going to change a lot. It's no longer going to ergodically fill the parameter space, but instead trace over the same space endlessly like this. And importantly, this has a particular value of PE and X. This has the exact same value of PE and X, right? So it's the same resonance, but I've just changed the initial value of the resonant phase, and now it's tracing out a different path through that same phase space. Meaning that if you were trying to orbit average over this orbit, you get a different value than if you were to orbit average over this orbit, which means that your orbit average is no longer something that is independent of your phases. It now explicitly depends on it. So we have to rethink the notion of an orbit average when we are in the presence of an orbital resonance. Now, you might think to yourself, Mel, maybe maybe they aren't that frequent. Maybe we don't care. Maybe in practice, they have such a small effect that we can get away with it. Maybe Lisa will never see these things. And I was really hoping this would be the case too, because then I could have finished my project way sooner. Turns out that we do, in fact, have to care about these. I've cut out again, a 2D slice of our parameter space that we evolved through, just in P&E, and I've plotted just as lines like these resonance surfaces where these things exist. What is most important to worry about is not the ones that have very high numbers, right? So where the ratios are very large. And the reason being is that these will tend to be exponentially suppressed. This is kind of a result due to the KEM theory, but it's also due to the fact that we have Fourier modes that are interacting, and Fourier modes tend to be exponentially suppressed as well. The ones that really, really matter and contribute the most to the physics here are the low order ones. So if you see two low numbers together, those are the ones you should worry about. Thankfully, it seems like a lot of them tend to group up near the last stable orbits. And as I mentioned, last stable orbits where everything's breaking down anyway, so maybe we're okay. If things are breaking down there too, fine, whatever. What really you should be scared of is a low order resonance that's far away from the LSO, so you have time to accumulate phase error. And that is exactly what this 2-3 resonance is. We also have this 2-4, which is pretty low order that we might need to care about too. But things that are very high, like this 610 or 6-8, probably have a much lower effect on the orbit. And this is the kind of thing we'll investigate. I've also plotted what a typical trajectory is like. As we can see here, it's not a case of if you hit one of these resonance surfaces, it's a case of when. And maybe you get lucky and Lisa turns off before you see the resonance and have to worry about this. But if you could see the entire inspiral, you will see it pass through every possible resonance surface on its way to the last stable orbit. So there's really no getting around these things. We will, in fact, have to model them. And so the way we've gone about this is I used a technique used by Martin originally in the paper of back in 2014, where you do kind of a partial averaging, right? So a partial knit, as we've called it. And the idea is that we find partially averaged equations of motion, where now, instead of, we do introduce some dependence on the resonant phase combination in particular, and we end up with equations of motion now in terms that look like this, where we have some oscillating terms, right? And again, we have terms that look very similar to what we had before. The main difference is the oscillations and the fact that we now have a new operator EMRis, which is the exact same operator as before, except you just make sure not to sum over the resonant value of n and m. So if you're near the 2-3 resonance, make sure not to evaluate at the n equals 2 and n equals 3, or any, what am I looking for? Any multiple of those, and you should be fine, right? So you just make sure not to go over the resonant tuples. And so that's the partial bit. And if we use this instead in the presence of an orbital resonance, this works fine. As you can see, we're just averaging through those oscillations quite nicely. We can put the oscillations back on. Everything looks a lot nicer. Importantly, nothing's blowing up, right? That's pretty important. And if we look at the convergence plots we have again, we recover the epsilon squared scaling that we expect in this plot and the epsilon scaling that we expect in this plot. So everything seems to be going well. The only downside is looking at the timing, how long it takes to produce these calculations. And you can see I've added the partial nit on here as well. And it's doing significantly better than the oscillating geodesics. That's no question. We're getting at least an order of magnitude or two speed up over the original one. The problem is that as we go to smaller and smaller mass ratios, we still have these orbital oscillations. And the larger the mass ratio, the more of these cycles. And so it'll take more and more time as we go to more and more extreme mass ratios, making this, again, not computationally efficient to use throughout the entire trajectory calculation. So the solution around this that I came up with literally right at the tail end, just as I was submitting the PhD, and I was so glad that it seemed to kind of work, is a very simple and I would say a very dumb solution to this, but it's this idea of a switch nit. The idea is that we're going to use the full nit when we're far away from the resonance, which is very, very fast, and then use the partial nit only when we're very close to the resonance so that we can resolve it and evolve it for as little time as possible. Now, very, very simple idea. The devil is always in the detail. When exactly do you make that switch? What counts as close to an orbital resonance, and so on and so forth? This is where the switching condition comes in, and this is where we got our collaborator Wojciech to go ahead and do a very, very long, in-depth calculation to figure out where exactly we should put this condition and what it should look like. I will spare you the details of that calculation. We can maybe discuss it a bit later. But what he ended up with is something that scales when, this, so say, for instance, the 3, 2, so n is equal to 3 minus 2 m, for this. When this combination becomes, so long as it's larger than this condition, which scales as with mass ratio to the 2/7, which is very interesting, times something that corresponds to the resonant time scale, which is a function of, again, of just PE and X, where it happens to occur. If it's bigger than this condition, use the full nit. If it is smaller than this condition, use the partial nit. And so recall that if we didn't do the switching, we end up with a phase error that would accumulate and grow to something that would scale with 1 over the square root of mass ratio. With this phase error, now we end up with an error that only scales epsilon to the 4/7. So this is, not as good as the epsilon to the 1, right? Obviously, 4/7 is not as small as 1, but it's still pretty, or not as large as 1, but still pretty good, and should be, in principle, be accurate enough for LISA data analysis. And we are then going to go and test this to make sure that that is roughly the case for some typical EMRis. And importantly, we can do this multiple times. We can do the switching procedure more than once. It takes quite a bit of effort and prep to do the procedure, but it can be done, as we'll show. So importantly, we want to show that this thing converges in the way predicted by Wojciech's calculation. And what we find is he predicts that the orbital elements should scale as epsilon to the 11/7. This was very difficult to actually find in the raw data itself. We couldn't compare it against the oscillating geodesic because, one, it was too slow, and two, it really got dominated by the epsilon scaling and epsilon squared scaling that we would see initially, making things difficult. The other thing is we couldn't just do it for one because the values that we get are very heavily dependent on the value of the resonant phase as we enter the resonance. And this we don't really have much control of when we initially start our calculations. So we had to do this for a whole bunch of different initial conditions, varying the resonant phase from 0 to 2 pi. And we then took the L2 norm to dot these plots. And I've also plotted also the minimum and maximum error between these for any given set of initial conditions for any given mass ratio. To give you an idea of the kind of variety that was here and how noisy some of the underlying data was. But once we do that sort of average, we can see that we do recover something that does roughly look like the 11/7 scaling that he predicted and the 4/7 scaling predicted for the phases. Again, it's not entirely perfect, but numerics have many sources of error and can be a bit funny sometimes, but it does give us confidence that this is converging fairly well. Importantly, it's not blowing up to epsilon to the 1 over the square root of epsilon, right? So it is decreasing with mass ratio, as always, making it a good candidate to use for EMRIs, which fills us with a lot of confidence that we can continue using this. And that's really the important thing. And so if we also look at the timing, we'll see we've gotten rid of a lot of the scaling with mass ratio issue we've solved for the timings before. This switch net coming across here. The problem, of course, being that this switching procedure and having to check this condition at every time step produces an overhead that's going to make the code run a lot slower, at least in our very unoptimal Mathematica implementation. So this overhead could certainly be reduced further, but at some point we needed to stop trying to optimize this and get something out that worked. But the idea is that it'll take roughly a constant 10 seconds per inspiral trajectory to evolve through a single resonance, as we'll roughly see. But importantly, though, the behavior of this will be well behaved as we go to smaller and smaller mass ratios. So we're going to do some tests on this. We're going to look at two case studies, both year-long EMRI signals that are going to be deep in the strong field, and that is going to pass through this really strong 2-3 resonance that I was talking about before. And so in order to show off like the jumps that I talked about, we are going to need first take the evolution of P. We're going to subtract off the leading order adiabatic behavior. And it's only when you do that you're able to actually see how large these jumps are in the orbital elements. As you can see by the scale on the plot, these are very, very small. And this is after subtracting off something. But you can definitely see where this 2-3 resonance is. You can zoom in and really see the oscillations here. And you can also see the difference between the various averaging schemes that we have used here. So in blue, we have the oscillating geodesics where you just have a ton of oscillations, right? And obviously that's going to be very, very slow, right? If you want to wait around for this, you got to look at, on the order of like maybe a couple of days to produce a single inspiral. So obviously that's not going to be viable at all. If you instead use the partial niche, which is in orange, right? We still have oscillations, but they are much, much smaller, and there's a lot less of them. So it's obviously much, much quicker, right? As you can see, our runtime has gone from several days to, about a little under 300 seconds. So on the order of a few minutes, which again is really not fast enough, but not too bad. And if we then compute the waveform for this, the mismatch between that and the oscillating geodesic waveform is actually very small. This is really, really good for laser data analysis, something that's order 10 to the negative 5. We want this to be, the mismatch to be as small as possible to ensure that we're going to get, not bias our parameter estimation. And so 10 to the negative 5 is very, very good. In principle, the benchmark you're usually looking for is something smaller than 10 to the negative 3 between two waveforms, more or less. Oversimplifying there for sure. Importantly, if you just use the full net, which I did not plot here at all, yes, you get something that's very fast. You also get a waveform that is terrible. Like 0.3 is just unusable. You cannot use this at all. So just forget about using the full net here. But then if we use our switch net, and you can see very effectively where this comes in. So this is in green, right? It's averaging out everything as it's far out here. And it's only once you get in close to the resonance that you can see it then switches over to the partial net, lies on top of what the partial net would have done, and then goes right back to averaging everything out. And so that gives us at least another order of magnitude speed up here, going down to around 20 seconds for a full year-long inspiral. And you do sacrifice a little bit of accuracy in doing so, but the accuracy you sacrifice is pretty minimal and is still more than accurate enough for what we would need for laser data analysis. So that is if we go through one resonance. But what if we go through two? So here, I decided to use the switch net both once to go through a single resonance and use it twice to account for both the 2-3 and the 2-4. So here, the single resonance is just a switch net is in orange, and the one that includes both is in green. You can clearly see where the 2-3 resonance is in this inspiral. You would really have to squint to see the 2-4. That gives you an idea of how exponentially suppressed some of these resonances are. And if you recall the plot I showed before, there are two other resonances in here somewhere that are higher order, and I have no idea where they are. I cannot see them. But even this one, you really have to squint to see the difference. So again, you're looking at an order of days to use oscillating geodesics here. You could use the full nit. It would be very, very fast, but the mismatch is somehow even worse. It's absolutely terrible. But if you use the single switch, right, you only account for specifically the 2-3 resonance, just this one here. Then you end up with a runtime that's again of order 20 seconds, right, what I saw before, with a very, very low mismatch, right? That tells you something very good. And this is completely neglecting one of the resonances. If you include the second resonance, well, then the overhead on doing that increases the cost again. You spend also a bit of time resolving this resonance. And so your cost, more than doubles to include the second resonance. And sure, it's more accurate, but not by that much. So this gives us an indication that maybe perhaps, and again, we are using a toy model to drive these things, so we can't say this will be true of all EMRIs, but certainly the higher order resonances you probably aren't going to matter that much. You might be able to get away with only resolving the 2-3 resonance. That is a very, very tentative speculation at this stage. You'd really need to like tile the full parameter space to say that for sure, but you absolutely need to include the 2-3 resonance and probably also the 2-4. Anything higher than that, you can probably get away with not including. But again, a more rigorous study that uses a more realistic model that actually, look through this could tell us. And there's also a certain amount of like how much error are you comfortable having in your data analysis in the name of speed. This is also a discussion that would need to be had for the data analysis community. But anyway, that is everything. Hopefully I've stayed roughly to time because I've completely lost where my timer is. But I'll just show my conclusions here. So the idea is that we use near identity transformations to give us efficient EMRI trajectory calculations. And that gives you something that can be evaluated in less than a second by removing the oscillations from our equations of motion. But this technique will break down when you go near orbital resonances, which are very likely to occur. And so we modify the nit to remove all the oscillations except for the resonant ones, which we call a partial nit. And by far the best thing to do is to switch between the full and partial nit using a very precise use of switching condition. And so with that, thank you very much for having me, and we can move on to questions.
Wonderful. Thank you. Thank you very much, Philip, for this great webinar. Let me see. Let me start here for people in this call. If they have questions, please let me know. And then I'll check the YouTube.
Hi, Alejandro.
Yes. Go ahead.
Eduardo. Okay, yes. I have a question for Dr. Lynch. First of all, thanks for this. Sorry, Okay, now you can see. So thanks for this presentation. And I wanted to ask you, since I'm working on my master thesis, the overall goal is to model this orbital resonance in Kerr spirals. I'm building upon a paper from Sperry and Geyer from 2021, where they introduced a resonance model within the numerical clutch framework. So I wanted to ask you which you think are the main differences between your approach and theirs in terms of waveform generation and possibly if there is something else, because I only could think about maybe difference in the waveform generation and errors. So thanks.
Yeah, great, perfect. Yeah, I can definitely talk about that. In fact, a lot of what we do here is very much inspired a bit by the numerical kludge. We end up using the same waveform generation method as them, as it turns out, actually. But again, we focus mostly, the differences come for the trajectory calculation. So in our case, so for the numerical kludge, they are only doing things to adiabatic order. So they aren't including the post-adiabatic effects that we're including. And even then, the adiabatic order things that they have are approximated using PN expansions of the fluxes, which means they are somewhat ill-suited to go really deep in the strong field, but they will be able to give you an idea of roughly how an EMRI will behave, which was the spirit of the kludge models in the first place. So in that case, they are quite useful there. But what really differs is the model that was used by Sperry and Geyer is a jump model where they put a discrete jump in the dynamics in order to resolve the orbital resonance. They use it, they initially say that the jump is scaled by some constant factor, just as a placeholder. They know that this is obviously just an effective resonance model, and then in principle, the actual size of the jump will depend on the position in the parameter space and these sorts of things. But as a placeholder in that study, they end up using just a constant value for the jumps. But in principle, we could take, calculate what the jump should be from the cell force once it becomes available, right? Now, we tried actually to do a similar sort of idea where you do this like finite jump. Actually, no, sorry. In their paper, they are in principle doing a jump, but they smooth it out over a smooth transition window, if I remember correctly. That's what they do. It's in their later paper with Pretty Gupta and company where they do, they look at transient resonances where they actually say like, oh, actually the difference between doing the smooth thing and just putting a finite jump is basically the same, at least what they found. So sorry, just want to make that clarification. And then we did actually try to do like a jump like this, inspired by the formula given in that Hinder and Flanagan paper in 2009 that I referenced earlier. And this is like a bonus slide that I have here. Right, we have a similar sort of thing, right? Where we're using, we try to, in green, put in this sort of jump inspired by this formula using our model. And what we find is that consistently, like no matter what parameters we used, it was consistently underestimating this jump, which makes me think that, well, actually, we know this is in principle like a linear in the kind of a leading order approximation to what the full jump should be over time. So the idea being that as you just evolve the fullness to around here, you turn off the terms that are becoming singular. You definitely need to do that at some point. And then you just have a discrete jump here given by this formula and then continue evolving afterwards. But it always underestimates the jump. It's also difficult to know what the correct value of this Q-res should be exactly at that point. Even though we evolve all of them, we have to turn off some corrections that puts ebetic, and that might be messing with things too. But in principle, I think it's just that this term is just like the leading order term of some like better expression, that there might be some additional correction that roughly scales with like the ratio of the resonant harmonics over the average or something like this. We call this formula in our paper, or this principle in our paper, like lowercase delta, that some like this is linear in delta term, and there might be some like next to linear order expression in delta, which might give you the last little bit of a correction to put it back here. But it could also be the fact that our toy model, again, is not very physical. We found comparing this to some resonant effects that tended to slightly overestimate the size of resonant effects. And it could well be that this formula is a good enough approximation when one actually calculates like a proper self-force model. So that is also probably the case. But because we could never quite get it to line up, we just decided not to include it in this paper. And we were in principle hoping to like find what that additional correction was and maybe use that as a new work. So this is a thing that we're currently not working on, but we hope to circle back to try and find what that additional correction should be, and if it actually is as important as our toy model is maybe making it out to be. So I hope that helped answer your question. If you have anything else that I missed out on, do let me know.
Yes, thank you very much. Yes, very useful because, yes, as you said in the Sperry Guide paper, basically the resonance coefficients are free parameters in the model. So the point is how you should calibrate them. And this is what I was working in the last day. So, okay, thank you very much.
Thank you, Eduardo, for the question. And Philip, just to clarify, what you say, like overestimate or underestimate, in the plot that you're showing here, it looks quite well. So I don't understand the dephasing in some sense that is shown before, because if the trajectory, at least on average, looks well, then this little dephase. So just to clarify my question, on the left-hand side, it looks like it matches quite well, or you at least can make the jump match as well as you want. So what do you mean by that? Can you clarify that?
Sure. So because it's slightly underestimating here, it's getting the evolution of the orbital elements slightly wrong. And again, it looks like it'd be pretty small. In fact, even like all of this is already like pretty small when you look at the scale. But the problem is having the orbital elements off just a little bit results in you accumulating a phase error, which you can kind of see here, right? That at the jump, because you didn't fully do it, you end up accumulating phase error over time. I have some other plots with this, but we looked at the mismatch, and it ended up being like the waveform mismatch you ended up getting was on the order of like 10 to negative 2, which is like not terrible, right? It's significantly better than nothing, but it wasn't quite what we would need. We need something a bit better.
And just to clarify, it's because if I use just a constant for that window that's awake in the jump, let's say, it's just a matter of finding a better constant, or because a constant won't do the job. In some sense, what I'm saying is, okay, here it's a little bit below in the plot. Can I make it a little bit larger and then fix that phase? Or it's just because the model won't be able to match?
I guess it's because that constant, right, is going to depend on the parameter space. Like here, it depends on the value of the force and its modes, and that's going to be a function of PE and X. So if you try and fix it for one resonance, it's not guaranteed that if you change the parameter slightly and look at a different part of the parameter space, that would also correctly resolve it there. So you need a function that does it for essentially every part of the parameter space and is somewhat physically informed, which is why we try to use this expression, which does that allegedly. But it does pretty well too, right? Okay. But just doesn't quite get us there.
I see. Gotcha. Thank you very much. I think Lennox has a question. Please go ahead.
Yeah. Thank you for the talk. I wanted to just ask a question about maybe the fundamental idea in nits. And so wanted to ask if you could explain some more about the oscillations you showed in the plot of P against E. So you showed that there were like some circular oscillations and this featured throughout. So I was wondering, A, what do they correspond to physically? And B, when you average them out and you're left with the kind of trending yellow line that's also there, what does that leave you with? Like, so what do you have once you've averaged them out? And how does that help you in this whole process?
Yeah, so this is actually a very good question as to which is the more physical model in a way. Like, is oscillating geodesics more physical or is the knitted ones more physical? But in principle, they do just correspond to the fact that, you have equations of motion and these depend on rapidly oscillating phases. And so if you look at any of these, both E and P independently, and you just plot those, right, as a function of time, you also do just see these oscillations too. And this effect gets magnified when you plot P versus E, right, as you see here. But you still see them there as well. As to which is fundamentally more physical, I would say in a way it kind of doesn't matter because these oscillations end up being really small, right? So maybe oscillating geodesics is a more faithful representation of nature. I don't necessarily believe that it has to be, but maybe it is. But the point is, if the NIT is only an approximation, then it's a very good approximation, at least for the kind of data analysis you want to do with LISA. So again, it's not clear to me which is necessarily more faithful. Again, the oscillating geodesics also, only takes the force in, and that itself is only valid up to, some truncation area in mass ratio, and that's just due to the force model, right? Oscillating geodesics independently is, totally fine. The force model itself is approximated, and so the combination of the two is also in itself a kind of approximation that includes oscillations that, in principle, are kind of coming from higher order mass ratio corrections. And in a way, you can think of it as the NIT just pushing those back out, maybe to where they're quote unquote supposed to be. But I do think, as to which one is more physical, they're both just different descriptions. And what's important is the waveform that you get out, which is a gauge invariant quantity that we'll see and we'll measure, has so like differences that are so small, kind of doesn't matter. That's the thing we really care about physically. I'm not sure if that fully answered the question.
Yeah. So just a quick follow-up. You also showed that you could add the oscillations back in, and it matched rather well with the osculating geodesics. And so
Yeah.
I guess my question kind of is then, why not then use the red dash line? As in, why are you using are you using a yellow line in all these calculations? So if
Yeah,
you
well,
can
I
add
can't
it back in, then why not just use it? Why use the yellow line instead?
Sure. And the reason being is that for extreme mass ratios, these oscillations are all really, really small, and so it doesn't make much of a difference. But the reason why we can quote unquote add them back in, it overlaps on them very, very well, but not perfectly. As I said, like when we look at these convergence plots, this is essentially what we're doing. We're comparing the blue line to the dash red line, which is what these correspond to. And like there is still an error between them, but it's an error that scales really well at mass ratio and becomes very, very small. So if you don't include these, you end up with an error that scales as order epsilon, and epsilon is a pretty good scaling and scales very in a way that's very small. So it's just a case of it's one extra step that one will have to do, and less physics to worry about us in a way. And so you can somewhat get away without putting the oscillations back on, at least for EMRIs. This might be more important if you were to try to model like EMRIs, where these oscillations might become more considerable. But it's kind of outside the scope of what I was looking at in this work.
Yeah. Okay. Thank you.
Any other question from the coordinators here? Let's see if there's something over.
Yes, I have a very
yes, go ahead.
For Philip. First of all, very interesting the talk. So I was wondering because and maybe you mentioned, but I didn't got it. Is there any effect if the object that is orbiting the black hole is in the same direction? I mean, the angular momentum are aligned or not aligned at the beginning as the initial conditions, in the sense that the spinning black hole will have a different effect if the rotation is against the usual path. I don't know.
Yeah, that's absolutely correct, actually. So you have what is known then as retrograde orbit. The main effect, so there are several things that will change there. One, you're in a very different part of parameter space. Like this is now what's considered like the X value I showed before takes on negative values when you're here. And the most important thing, I think, is the fact that you end up with an innermost stable orbit or a last stable orbit that goes from being very close to the black hole to being much further out. It'll end up like transitioning to planet way sooner. So you can't really probe the same strong field physics that you could if it was going with the black hole. So in a sense, we always kind of show off the really, really cool things when it's like going with the rotation of the black hole, because you get like even cooler strong field dynamics. But it is absolutely possible that you could end up with EMRis that form with opposite angular momentum. What ends up happening is they'll end up like plunging sooner and giving off in a way because they don't get into the strong field, like weaker signals. So we're probably less likely to see them in a way, but it's definitely not impossible that we would still see them in LISA.
So, but then in both cases, you have the same oscillation effects and.
Oh yeah, we still see the same oscillatory behavior. The oscillations will change slightly, obviously, but this will work in both cases if you apply it consistently.
Okay, thank you.
Thank you. Okay, I think we're past the hour, but since I'm the host, maybe I can ask the last question just for the future of the field. So in principle, Philip, what would be your ideal goal? Like I would imagine that for modeling these EMRis, we might not want to have a prescription and then switch back to something like in the Frankenstein monster. In principle, you think in the prescription that you showed at the beginning, we'll have the second order, and then in principle we would be able to compute this analytically or some prescription such that we can just let it evolve, and then there is just one single prescription. It's more an open-ended, idealistic question. Do you think we have a prescription that will be able to capture all of these effects, or will we always have to resource to these effective models as Eduardo was talking about, or these prescriptions where we switch and back and forth, constantly analyzing the orbit?
Yeah, I think because I think it does come down ultimately to the fact that the definition of an orbit average changes on a resonant orbit. And you're not going to get one wholesome prescription that can just go through the whole thing and also be computationally efficient and not have these oscillations. But that's
just the adiabatic, right? Just to clarify, that would be just because you took an average. Like in principle, the adiabatic, if you don't do the adiabatic, then you don't have that, right?
Yeah, you can use osculating geodesics, and that will capture all the resonant orbits the whole way through. But again, the problem I was highlighting was that it's just very, very slow. I guess in principle, if you wanted like a golden, some golden waveform model to compare against, as I was kind of doing before, then you could just evolve everything with osculating geodesics and just compare to make sure that your averages and things were still working. But in principle, I think the thing that would be most useful on the data analysis end is not something that's very, very slow, but hyper accurate, but instead like some sort of effective resonance model, as was mentioned before, that can just very easily use the full net as much as possible, just jump to accommodate the resonance and then continue on while maintaining very, very faithful phase accuracy. And of course, you'd want like oscillating geodesics to compare against at the end to make sure it works. Great.
Thank you very much, Philip, for joining us today, for your time on this very nice webinar. Thank you all for attending today's Law Physics webinar, which, Roberto, can you remind me which one is this? 168?
68, yes.
Okay, cool. Stay tuned for the next one, and then our next season will start sometime in September or something like that. Thank you very much, and thank you all for attending today. Thank you, Philip.